Welcome to the AI Checkpoints. I'm your host, ready to explore the fascinating and sometimes, frankly, mind-bending world of artificial intelligence. Today, we're embarking on a deep dive into a challenge that might genuinely surprise you, especially if you, like many, think AI is all about precision and predictable outcomes. We're talking about getting large language models, your GPTs, your LLMs, to produce the exact same output twice. You'd think if you ask an LLM the same question, especially if you turn down its creativity or temperature all the way to zero, you'd get an identical answer every single time, right? Well, it turns out it's not always that simple. In fact, it's often not simple at all.
That's absolutely right. The concept of reproducibility is foundational, not just to scientific progress, but to building reliable and trustworthy AI systems. Yet, as a recent article from Thinking Machines Lab points out, its title, Defeating Nondeterminism in LLM Inference, come out September 10, 2025, from Horace He and collaborators, achieving truly reproducible results from LLMs has been remarkably difficult. Our mission today is to peel back the layers, unpack why this seemingly trivial issue has persisted, challenge some common assumptions we've all probably made, and ultimately reveal how these researchers are finally solving this puzzling problem.
So settle in, because you're about to get a behind-the-scenes look at what's really going on when you interact with an LLM. And you'll discover why the seemingly small technical detail has surprisingly big implications for everything from rigorous scientific research to the personalized AI experiences we're all coming to rely on. Let's dig in. Okay, let's unpack this.
Many of us have probably noticed that if you prompt a model like ChatGPT with the same question multiple times, you often get slightly different results. For most creative or open-ended prompts, we typically assume that's due to something called sampling, where the model probabilistically selects tokens, giving it that touch of randomness. But what the Thinking Machines Lab article highlights is something far more surprising and, honestly, a bit of a head-scratcher.
Indeed, it's truly counterintuitive. Even when you explicitly set the temperature parameter down to 0, which, as you mentioned, theoretically means the LLM should always choose the highest probability token, a process we call greedy sampling.
Right, just pick the best one. It's just the most likely word every time LLM APIs are still not deterministic in practice. You'd expect perfect consistency, but you just don't get it. And this isn't just some quirk of the big commercial APIs either. The paper references multiple past discussions on this. Even if you run inference on your own hardware with popular open source libraries like VLLM or SGLang, you're not guaranteed deterministic sampling.
Wait, so even when I tell the model, just give me the most likely word, no creativity, no randomness, it still can't give me the same exact output every time? That genuinely blows my mind. I always thought temperature 0 was the golden rule for reproducibility. So why is this happening if it's not just the model being creative? A common hypothesis, which I certainly believed, and one noted by Thinking Machines Lab, is the concurrency plus floating point idea. The thought goes like this. Floating point arithmetic in GPUs, because of its finite precision and rounding errors, is non-associative, meaning A plus B plus C might not perfectly equal A plus B plus C. Combine that with massive parallel operations on GPUs, where the order of calculations can shift, and you could easily get different results. Sounds perfectly logical, right?
It does sound logical, yeah, and you'll find this hypothesis repeated quite often in discussions about non-deterministic GPU behavior. But what this article reveals is that it doesn't tell the full story, especially for LLM inference. Consider this. If you run the exact same matrix multiplication on a GPU with the exact same input data repeatedly, you will always get bitwise equal results.
Oh, really? Always?
Always. Despite using floating points and massive concurrency. This immediately signals that while floating points are involved, the concurrency plus floating point hypothesis on its own misses a critical piece of the puzzle for why LLMs specifically show this kind of non-determinism. The very definition of what deterministic means for LLMs is tricky, The paper lists four seemingly contradictory but actually true statements about different levels of determinism depending on context. It's a nuanced problem.
Okay, so the concurrency plus floating point idea, while plausible, isn't the full picture for unpredictable non-determinism. But before we dive into the true culprit, we do need to appreciate the foundational quirk that allows for any numerical differences to occur in the first place, what the Thinking Machines Lab article calls the original sin of floating point non-associativity. This is key because it's why there can be numerical differences even before we get to why those differences become unpredictable.
That's exactly right. Think of it like this. With floating point numbers, the order of operations can actually change the result, sometimes quite dramatically. The paper provides a classic example,
Right.
0.1 plus 1e20. That can result in 0.
Right.
But if you do it differently, 0.1 plus 1e20, that can result in 0.1.
Huh.
This happens because floating point numbers have a limited sort of dynamic level of precision. Imagine you're doing math with a calculator that only shows, say, 3 significant digits. If you add a tiny number like zero point 0.1 to a huge number like 120, that's 1 followed by 20 zeros, that zero point 0.1 might simply get swallowed up and rounded away because it's so much smaller.
Okay, yeah.
But if you do the subtraction first, 1A2020 becomes 0, and then 0.1 plus 0 is clearly 0.1. So the order totally changed the outcome, effectively destroying information.
So every time floating point numbers with very different scales or exponents are added or processed, information can be lost or rounded differently depending on the exact order of operations. The article provides an extreme example with just a small array of numbers, showing there can be, 102 possible different results for summing that array depending on the order?
Yeah, 102.
That's a staggering amount of potential variation from something that looks like simple addition. Does this original sin essentially set the stage for all the unpredictable behavior we see?
Exactly. It's the fertile ground. It creates the potential for variation. Like, imagine building a house where the exact order you mix the cement can subtly change its strength. The core materials are the same, but the process introduces variability. So while floating point non-associativity is the underlying cause for non-identical outputs, it doesn't directly explain nondeterminism, which is why floating point values get added in different orders unpredictably from one run to the next. The real answer, as the paper delves into, lies in how the low-level programs that execute on the GPU, what we call kernels, are implemented, and how they don't always add numbers in the same order unless specifically designed to do so.
Okay, so we've established that floating point math sets the stage for numerical differences. And Thinking Machines Lab clarifies that while concurrent atomic adds these specialized operations that can indeed make a kernel non-deterministic.
Right, those can cause it.
They can, but they are actually not necessary and typically not present in the vast majority of kernels during an LLM's forward pass. This means that from the inference server's perspective, the forward pass itself is actually run-to-run deterministic if given the exact same set of inputs. So, if the math can be precise when needed, and the forward pass is inherently deterministic, then where on earth is the unpredictable non-determinism coming from? This is the core mystery.
This is where it gets really interesting and where the crucial insight from the Thinking Machines Lab comes in. The forward pass might be deterministic, is given the exact same inputs, but the missing piece is something called batch-invariance. Your individual request's output does depend on other parallel user requests being processed at the same time, not because of information leaking between users, but because the forward pass lacks batch-invariance. This means that when the batch size, the number of user requests being processed together, changes, each individual element within that batch can get a slightly different result.
That's a truly sneaky form of non-determinism. Mathematically, if you're doing matrix multiplication, the calculations for one item in a batch should be entirely independent of another item in the same batch. It should just be parallel work.
You'd think so.
But the paper demonstrates empirically that this isn't true in practice. They show a specific matrix multiplication where taking the first element of a batch, out 1, gives a different result than performing a larger batch multiplication, and then extracting the first element, out 2, with a difference of tensor 0.269.250 divides CUDA 0.0. Wow, that's not a tiny difference.
Not at all. So it's still run-to-run deterministic for a given batch size, but it's not batch-invariant.
Why would this be the case? Why wouldn't those individual calculations be isolated? How does adding more unrelated work change my specific calculation?
Exactly. The critical takeaway is that from an individual user's perspective, the server's load, and thus the batch size their request is processed under, is effectively non-deterministic. You can't control or predict how many other people are hitting the server when your request goes through. When you combine this lack of batch invariance in the kernels with the unpredictable nature of the system load, you end up with a fundamentally non-deterministic system from the user standpoint. And interestingly, this primary reason for LLM inference non-determinism varying load and batch size isn't even unique to GPUs. It affects CPUs and TPUs too. It's a systemic issue in how parallel computations are often optimized for speed over perfect consistency.
Okay, so knowing that variable batch size and the lack of batch invariance in our kernels, those tiny specialized GPU programs, is the primary antagonist here, the obvious next question is, how do we fix it? How do we force these LLMs to be consistently predictable?
Right. How do we get actual determinism? The solution, as proposed by Thinking Machines Lab, is to achieve batch invariance across the critical operations. This means ensuring every kernel produces the same bitwise result, regardless of the batch size or how requests are grouped together. They focus on 3 key operations. RMSNorm, matrix multiplication, and attention.
All right, let's take them one by one. RMSNorm.
Okay, RMSNorm. This is a normalization layer, pretty crucial for stabilizing training and inference in LLMs. The standard data parallel strategy, where basically each GPU core handles one element for the batch, is naturally batch-invariant. That works fine. The challenge often arises with small batch sizes. To improve efficiency, engineers might switch to different, highly optimized reduction strategies, ways of summing up numbers across the cores. But these faster strategies, unfortunately, can break this invariance. So the fix is to consistently use a single, robust reduction strategy that provides enough parallelism for all batch sizes, even the small ones. This might mean accepting some minor performance trade-offs sometimes, but it prioritizes consistency.
Makes sense. Consistency over speed in that specific case. Okay, moving on to matrix multiplication. Similar story.
Pretty similar, yeah. Data parallel strategies generally work well for large matrices. However, with smaller batch sizes or specific matrix dimensions, the GPU might employ clever optimization tricks, things like split-k matmul or switching to different internal tensor core instructions.
Which are basically specialized ways the GPU does math faster.
Exactly, they squeeze out more speed. But these optimizations, while great for performance, can change the order of operations slightly and introduce that non-invariance again. So the pro solution here is to compile one specific kernel configuration for matrix multiplication and just use it consistently for all shapes and sizes. The paper notes this might incur maybe about a 20% performance loss compared to highly optimized libraries like Kublaze, but importantly, they found it's often not disastrous for overall LLM inference time.
Okay, manageable trade-off potentially. And finally, the big one, attention. That seems like where things could get really complex.
And they do. Attention is the mechanism allowing the LLM to focus on different parts of the input. It involves complex calculations, reductions over both feature and sequence dimensions, plus all sorts of inference optimizations like chunked prefill for handling long inputs efficiently. The core principle for batch invariance here is that the order things get summed up for any given token must not depend on how many other tokens from its own sequence are being processed at the same time in that batch. The paper points out that some implementations explicitly handle the KV cache, which is like the model's short-term memory of previous tokens.
Right, the context.
Yeah, the context. Handling that separately from the current tokens being processed actually breaks batch invariance because of boundary conditions at the edges where the cache data meets the new data.
Ah, subtle. So how do they fix that?
The fix involves carefully updating the KV cache and its corresponding page table before the main attention kernel runs. This ensures a consistent data layout every time.
Okay, but you mentioned another wrinkle during the decode stage.
Yeah.
When it's generating word by word.
Right. During decoding, the query length is very small, often just one token. This often necessitates different strategies like split KV or flash decoding, which are super efficient for these specific short queries. But guess what?
They break batch invariance again.
You got it.
Uh-huh.
They break batch invariance. And what's fascinating here is that unlike RMSNorm or matmuls, where you might just pick one fixed kernel configuration, a simple fixed number of splits won't work for attention in the decode stage because the sequence length keeps changing.
So what's the solution there?
The solution for attention in decode is clever. Adopt a fixed split size strategy rather than a fixed number of splits. This guarantees an identical reduction order, an identical way of summing things up, regardless of how many tokens are being processed in parallel within a batch for that decoding step. It preserves batch invariance. This requires specific, targeted changes to the attention implementation, like the changes being upstreamed into projects such as flex attention, to truly ensure deterministic results across all these complex operations. It's definitely not just flipping a switch. It's real engineering work.
This all sounds very technical, involving deep dives into kernel implementations, but what's the real-world impact? Like, can you actually see the difference? The Thinking Machines lab ran experiments, right?
Yeah.
Using that Feynman prompt.
They did, and the results were quite stark. They used a Quinquenth 3235B A22B Instruct 2507 model, sampled 1,000 completions at temperature 0 with the prompt, "Tell me about Richard Feynman." With the standard non-batch invariant kernels, the kind most systems use, they generated 80 unique completions out of 1,000 requests.
80 different answers from the same prompt at temp 0.
80. Think about that. The divergences often began surprisingly late in the output, maybe around the 103rd token. For example, most completions would say Queens, New York, but 8 of them switched to New York City. Small differences, but differences nonetheless. However, when they enabled their newly developed batch invariant kernels, All 1,000 completions were bitwise identical,
Wow.
not just similar perfectly, exactly the same. It really demonstrates the direct, tangible impact of addressing this batch invariance issue.
That's an incredible difference. From 80 unique answers down to one single consistent answer. Okay, but for practical use, the performance question looms large. Are these batch invariant kernels prohibitively slow? Does determinism cost too much?
That's always the crucial question, isn't it? While they noted the kernels weren't yet heavily optimized, the initial performance tests provide some promising context. An unoptimized deterministic VLLM was indeed slower. It took about 55 seconds compared to 26 seconds for the default non-deterministic version on their test.
Oof, that's more than double.
It is. But with just an improved attention kernel implemented, that time came down significantly to 42 seconds. The paper emphasizes that even at this early stage, the performance hit is not disastrous for usability, especially considering the benefits. And ongoing optimization efforts will likely close that gap further. What's also fascinating is they observe this jigsaw pattern in performance across different batch sizes with the deterministic kernels. It's caused by quantization effects interacting with the fixed configurations. Normally, engineers smooth this out by dynamically changing things like tile sizes, but for determinism, they had to keep it fixed, hence the initial jagged performance.
Interesting. So performance is a factor, but maybe not a deal breaker and likely to improve. Now, beyond just getting consistent outputs, which is obviously a huge win, the article highlights a potentially profound benefit for AI research, true on-policy RL. For those less familiar with the nuances of reinforcement learning, what exactly does on-policy RL mean, and why is achieving true on-policy so significant?
Yeah, this is a really important point for researchers and anyone actually training these models. In reinforcement learning, an agent learns by interacting with an environment, getting rewards or penalties. On-policy RL basically means the agent is learning directly from its current behavior, the data it's generating right now, using its current strategy or policy. Off-policy RL, by contrast, means it learns from data generated by a different or older policy, maybe from past experiences.
Okay.
Traditionally, the subtle numerical differences we've been talking about, the ones that arise between the LLM's training environment and its inference environment, due to things like batching, implicitly turn what should be on-policy RL into a kind of messy, unintentional off-policy RL.
Ah, because the live data isn't exactly what the training algorithm expects.
Precisely. This mismatch can lead to instability and make training much harder. By achieving bitwise identical results between the sampler, the LLM generating responses, and the trainer, the system learning from those responses, which deterministic inference enables, researchers can now achieve true on-policy RL. Their experiments show that without this determinism, training rewards could collapse because of this misalignment. But with true on-policy execution, training proceeded smoothly. And crucially, the KL divergence, which measures how different the probability distributions are between the sampler and trainer, stayed flat at 0, confirming they were perfectly aligned. It means a much more reliable and efficient research and development process.
So what does this all mean for you, the listener? What we've just done is a deep dive into an issue that often gets sort of papered over in machine learning development, the surprising and often frustrating non-determinism of LLMs. We've gone from just noticing different outputs to understanding how floating point non-associativity creates the potential for differences, and then uncovering the true culprit for the unpredictability. The lack of batch invariance in those low-level kernel operations processing your requests.
And the truly exciting part is the practical solutions proposed by Thinking Machines Lab. They demonstrate that with targeted, meticulous engineering, it's actually possible to defeat this non-determinism across key operations like RMSNorm, matrix multiplication, and attention. This leads to truly reproducible LL inference, moving from a system that might give you 80 different answers to the same question, to one that consistently provides a single, bitwise identical output every single time. As the paper powerfully concludes, we reject this defeatism. With a little bit of work, we can understand the root causes of our non-determinism and even solve them.
It really makes you wonder, doesn't it? What other assumed non-deterministic behaviors in complex AI systems might simply be solvable engineering challenges, just waiting for a deep dive like this one for someone to dig in and find the actual root cause? It's a powerful reminder that fundamental understanding and careful implementation can lead to profound improvements, not just in consistency, but potentially in the very foundations of AI research and deployment. Thanks for joining us for this deep dive. Hit like and subscribe if you like the content. See you next time.